Assalamualaikum. We are from Group L and today we will present about our group project topic Hybrid Deep Learning for Electricity Load Forecasting LSTM XGBoost applied to smart meter data. First of all, my name is Farah Amira and my metric number is 2317648. Okay, first we will take a look at our project background. So this project focuses on electricity load forecasting within a smart grid environment. With the rapid digitalization of power system and the adoption of smart grid technologies, electricity consumption data is continuously generated in large volumes. So this data is typically recorded as time series data and reflects dynamic patterns influenced by system operations, environmental conditions, and user behavior. Accurate electricity load forecasting is essential because it supports efficient demand-supply balancing, energy efficiency planning, and reliable grid operation. Inaccurate forecasts can lead to system instability, energy wastage, or increased operational costs. But however, electricity load data is often non-linear, time-dependent, and non-stationary, which makes forecasting a challenging task. Okay, moving on to the machine learning approach. Traditional statistical forecasting techniques such as linear regression and tree-based models often struggle to model the complex characteristic of real-world electricity consumption data. This is because smart grid data exhibit sudden fluctuations, daily and hourly patterns, and complex interaction among multiple features. As a result, machine learning and deep learning approaches have gained popularity due to their ability to model non-linear relationships. So in this project, long short-term memory networks are used because they are effective in capturing temporal dependencies in time series data. But however, LSTM models can still suffer from residual errors and sensitivity to noise. To address this limitation, XGBoost is incorporated due to its strong performance in handling structured data and nonlinear relationships. So by combining LSTM and XGBoost, a hybrid learning framework is proposed to enhance forecasting accuracy and robustness. Okay, now for data analysis, we will first take a look at the dataset overview. The dataset used in this study is the Smart Grid Real-Time Load Monitoring dataset obtained from Kaggle. The dataset consists of 50,000 observations representing real-time electrical and environmental measurements collected from a smart grid system. The dataset includes electrical parameters such as voltage, power factor, frequency, and power consumption, as well as renewable energy inputs like solar and wind power. Environmental factors such as temperature and humidity are also included, and the primary target variable in this study is power consumption, measured in kilowatts. The initial data inspection confirmed that there are no missing values, eliminating the need for imputation during preprocessing data. Okay, now for exploratory data analysis. It was performed to understand the statistical characteristics and relationship within the dataset. Descriptive statistical analysis showed that voltage remains relatively stable, while current and power consumption exhibit higher variability, reflecting fluctuating load demand. Renewable energy inputs such as solar and wind power display wide range, highlighting their intermittent nature. Pairwise feature visualization reveals several nonlinear relationships and clustered patterns among electrical parameters, and correlation analysis showed moderate inter-feature correlation without severe multicollinearity. So, based on this observation, it was concluded that linear modeling assumptions may be insufficient, justifying the use of advanced nonlinear learning models such as LSTM and XGBoost. Okay, now for feature engineering and pre-processing. Based on the exploratory analysis and domain knowledge, feature selection and pre-processing were performed. The timestamp column was removed as it is non-numeric and not directly informative for regression models. The predicted load column was excluded to prevent information leakage, as it is derived from the target variable, and the current feature was also removed due to physical redundancy since electrical power is directly related to voltage and power factor under relatively stable grid conditions. Okay, now feature scaling was applied to improve model performance and training stability. Standard scalar was used for traditional machine learning models and XGBoost, while min-max scalar was applied for LSTM models. And finally, the dataset was split into 80% training data and 20% testing data to ensure fair and consistent model evaluation.
Okay, so for our methodology, first we prepare the dataset by removing the timestamp, predictor load, and curve features to avoid redundancy and data leakage. Then our target variable will be power consumption in kilowatts. And then we split the data into 80% for training and 20% for testing. We apply feature scaling using min-max scalar for the LSM model and standard scalar for the machine learning model. Okay, so for the baseline comparison, we implemented linear regression and discrete regression. This helped us understand the performance improvement achieved by more advanced methods. After that, we built an LSTM model with two stacked LSM layers and dropout to capture temporal dependencies in the data. Then we train using the Adam optimizer and mean square error loss. After training it, we calculate the residual errors between the actual values and LSTM prediction. Then this residual were learned by XGBoost model to capture nonlinear patterns that the LSTM could not fully model. Finally, our hybrid prediction was produced by adding the XGBoost residual output to the LSTM prediction. And then all our model were evaluated using May, MSE, RMSE, and R squared to compare their performance daily.
For this section, the focus is on evaluating the performance of all implemented models and analyzing how well the hybrid LSTM XGBoost approach performs compared to traditional and standalone machine learning models. The discussion includes both numerical evaluation metrics and visual analysis to better understand the model behavior. Now, I'll discuss the performance results across all models. From the table, linear regression shows the poorest performance with the highest MAE and the lowest R squared. This is expected because linear regression assumes a purely linear relationship between input features and power consumption. However, smart grid data is inherently nonlinear and time-dependent, which violates this assumption. Decision tree regression improves performance by capturing nonlinear relationships. However, it still lacks awareness of temporal dependencies and tends to overfit specific patterns in the training data. The LSTM model performs better because it is designed for time series data. By using memory cells and gating mechanisms, LSTM can learn temporal dependencies such as consumption trends over time. However, LSTM predictions tend to be smooth, meaning it struggles with abrupt load changes and complex nonlinear fluctuations. XGBoost further improves accuracy by learning nonlinear relationships through an ensemble of decision trees. It focuses on correcting prediction errors iteratively, which makes it more robust than single-tree models. The hybrid LSTM XGBoost model achieves the best performance across all metrics. This confirms that combining temporal modeling from LSTM with nonlinear residual correction from XGBoost leads to more accurate and stable predictions. Next, we'll take a look at the actual versus predicted scatter plot. In this figure, the x-axis represents the actual power consumption, and the y-axis shows the predicted values from the hybrid model. The red dashed line indicates perfect prediction. Most data points lie close to this ideal line, indicating that the model predicts power consumption accurately across a wide range of values. The strong linear alignment shows that the model generalizes well, rather than performing well only in a narrow operating range. Although a few outliers exist, they are rare and do not significantly affect overall performance. This confirms that the hybrid model maintains consistent accuracy even during high and low load conditions. Moving on, we're going to examine the residual behavior to assess prediction bias. This histogram shows the distribution of residuals, calculated as the difference between actual and predicted values. Most residuals are centered around 0, indicating that the model does not consistently overestimate or underestimate power consumption. The roughly bell-shaped distribution suggests that the errors are random rather than systematic. This is a desirable property because systematic bias would indicate missing patterns in the model. The limited number of extreme residuals shows that large prediction errors are infrequent, which is critical for maintaining grid stability in real-world application. Lastly, we're going to look at the time series residual correction. The gray line represents residual errors from the LSTM model alone. These errors fluctuate significantly, showing that LSTM struggles with sudden changes and nonlinear behavior. The green line shows the residual predicted by XGBoost. The close alignment between the two indicates that XGBoost successfully learns the error structure left by LSTM. When these residual corrections are added back to the LSTM predictions, the final hybrid output has significantly reduced error volatility. This visual evidence supports the numerical improvement observed in the evaluation metrics. To conclude, I'll summarize the key outcomes of this project. This project demonstrates that hybrid machine learning models can significantly improve short-term electricity load forecasting in smart grid environments. While traditional and standalone models capture partial patterns, they are insufficient to fully model the nonlinear and temporal complexity of real-world power consumption data. The hybrid LSTM XGBoost model effectively combines temporal learning and nonlinear error correction, leading to improved accuracy, stability, and robustness.
To wrap up, we identify 4 key areas to take this model to the next level. First, architecture upgrades. We'll transition it to bi-LSTM and attention mechanism to better track global dependencies and focus specifically on high-demand peak periods. Secondly, data expansion. We plan to use multi-step sequences to capture weekly cycle and integrate external features like weather and calendar events for higher accuracy. Third, optimization and forecasting. We will implement Bayesian optimization for automated tuning and move toward probabilistic forecasting to provide uncertainty estimate for better risk management. Finally, cloud deployment. The goal is to migrate this system to cloud platform and it allows us to scale and process live smart meter data in real time.
Okay, now I will demonstrate the deployment part of our project. The main objective of the deployment is to make the trained models usable in a real-time and interactive environment without retraining. So after complete all the trainings, the model were saved for later use. The LSTM model was saved in HDF5 format and the XGBoost model was saved in JSON format. Meanwhile, the hybrid model was saved using Python pickles library. Okay, next, in the same folder, we also create a Python file called app.py, which handles model loading, user input processing, and prediction logic. And for the deployment, we use Streamlit because it allows fast and simple deployment of machine learning application using only Python without complex front-end development. And this application runs locally on a Windows machine. To start the app, we first need to open our command prompt in the laptop and find the path of the file first. And then we can continue to open the Streamlit by typing this command. And the Streamlit will open the apps automatically in the web browser. This is the Streamlit interface. Users are required to enter exactly 12 input features, which match the features used during model training. Okay, for the demonstration, I will use the following sample value. Okay, let's say the first feature is hour, so I will put 14. And the second feature is day, I will put 3. And month, 7. For the fourth feature is the temperature, 31.5. And humidity here is 68%. Wind speed here is 2.1. Feature 7 is solar radiation 420. Feature 8 is rainfall, which is only 0. Feature 9 is previous load 3.25. Feature 10 is maximum load, which is 4.1. Feature 11 is minimum load, which is 2.8. And feature 12 is for load at previous hours, which is 3.1. Okay, next, after entering all the values, I will click the predict button and it will show predictions complete. And after that, it will show the LSTM prediction, XGBoost prediction, and hybrid prediction. That's all from us. Thank you.